Hello, hello, and welcome to Ether Cosmology Reading Night, Space Audits ADL, and the crew. Thank you, everyone, for being here to listen in. Although, heads up, just like I always say on Thursday night, this is Reading and Research Night where we do live on the spot reading and research. It's not necessarily about, having a presentation for you, the audience. It's not about making it, in a nice little package or whatever. This is us doing live on the spot research. And at times we may go on tangents. At times we may divert from the reading material even. But it's just to give you a glimpse kind of into our process. And yeah, tonight we're going to be reading from Shankar's book on physics. We're going to basically just read straight through. We're going to just dive into this physics book. We had a few people talking about wanting to go through physics kind of from the ground up, so that's what we figured we would start with on tonight. So that's what we're doing, and here we go. Kinematics and dynamics, section 1.2. Should I start us off? Does anyone else want to read? Or
If you want to intro us off, or go ahead and start us off, bro.
Cool. Kinematics and dynamics, section 1.2. We're skipping section 1.1 because it's just kind of talking about the book, and this will just kind of save us some time. We are going to be studying Newtonian mechanics. Standing on the shoulders of his predecessors, notably Galileo, Isaac Newton, plays us on the road to understanding all the mechanical phenomena for centuries until the laws of electromagnetism were discovered, culminating in Maxwell's equations. Our concern here is mechanics, which is the motion of billiard balls and trucks and marbles and whatnot. You will find out that the laws of physics for this entire semester can be written down on the back of an envelope. A central purpose of this course is to show you repeatedly that starting with these few laws, you can deduce everything. I would encourage you to think the way physicists do, even if you don't plan to be a physicist. The easiest way to master this subject is to follow the reasoning I give you. That way, you don't have to store too many things in your head. Early on, when there are 4 or 5 formulas, you can memorize all of them and you can try every one of them until something works. But after a couple of weeks, you will have hundreds of formulas and you cannot memorize all of them. You cannot resort to trial and error. You have to know the logic. The goal of physics is to predict the future given the present. We will pick some part of the universe that we want to study and call it the system, quote unquote. And we will ask, what information do we need to know about the system at the initial time, like right now, in order to be able to predict its future evolution. If I throw a piece of candy at you and you catch it, that's an example of Newtonian mechanics at work. What did I do? I threw a piece of candy from my hand in the initial conditions where I released it, and with what velocity that from my hand, and its initial conditions are where I released it, and with what velocity. Okay, thank you. That's what you see with your eyes. You know it's going up, it's going to follow some kind of parabola, and your hands get to the right place at the right time to receive it. That is an example of Newtonian mechanics at work, and your brain performed the necessary calculations effortlessly. You only have to know that the candy's initial location and the candy's in the initial velocity. The fact that it was blue or red is not relevant. If I threw a gorilla at you, its color and mood would not matter. These are things that do not affect the physics. If a guy jumps off a tall building, we want to know when and with what speed he will land. We don't ask why the guy is ending it all today. That is a question for the psych department. So we don't answer everything. We ask very limited questions about inanimate objects, and we brag about how accurately we can predict the future. Kind of fun. The Newtonian procedure for
Nice.
predicting the future given the present has 2 parts, kinematics and dynamics. Kinematics is a complete description of the present. It's a list of what you have to know about a system right now. For example, if you're talking about a piece of chalk, you will want to know where it is and how fast it's moving. Dynamics then tells you why the chalk goes up or why it goes down, and so on. It comes down due to the force of gravity. In kinematics, you don't ask for the reason behind anything. You simply want to describe things the way they are, and then dynamics tells you how and why the description changes with time. I'm going to illustrate the idea of kinematics by following my preferred approach. starting with the simplest possible example and slowly adding bells and whistles to make it more and more complicated. In the initial stages, some of you might say, well, I've seen this before, so maybe there's nothing new here. But that may be true. I don't know how much you have seen it, but it is likely that the way you learn physics in high school is different from the way professional physicists think about it. Our priorities and the things that we get excited about are often different, and the problems will be more difficult. Section 1.3, Average and Instantaneous Quantities. We are going to study an object that is a mathematical point. It has no size. If you rotate it, it will look the same, unlike a potato, which will look different upon rotation. It's not enough to just say where the potato is, you have to say which way its nose is pointing. The study of such extended bodies comes later. Right now, we want to study an entity that has no spatial extent, a dot. It can move around all over the place. We're going to simplify that too. It can move around all over space. We're going to simplify that too. We're going to take an entity that moves only along the x-axis. So you can imagine a bead with a straight wire going through it, which allows it to only slide back and forth. This is about the simplest thing. I cannot reduce the number of dimensions, but I can make the object simpler than a mathematical point. To describe what the point is doing, we pick the origin, call it x equals 0, and put some markers along the x-axis to measure distance. Then we will say this guy is sitting at x equals 5. Now, of course, we have units, and the unit of the length is going to be the meter. The unit for time will be a second. Sometimes I might not write the units, but I have earned the right to do that, and you haven't. Everything has got to be in the right units. If you don't have the units, and you say the answer is 42, then we don't know if you are right or wrong. Back to the object. At a given instant, it's got a location. We would like to describe the object's motion by plotting a graph of space versus time. A typical graph would be something like figure 1.1. Even though the plot is going up and down, the object is moving horizontally back and forth along the spatial x-axis. When it is at A, it's crossing the origin from left and going to the right. Later, at B, it is crossing back to the left. In the language of calculus, x is a function of time, x equals x of t, and the graph corresponds to some generic function that doesn't have a name. We will also encounter functions that do have a name, like x of t equals t, x of t equals t squared, and x of t equals a sine of t, cosine of t, and so on. Trajectory, so that's a chart or showing the trajectory of a particle. The position x of t is measured vertically and time t is measured horizontally. So consider v, the average velocity of an object, given by v equals x times t2 minus x times t1 over t2 minus t1, where t2 is greater than t1, are two times between which we have chosen to average the velocity. In the example in figure 1.1, v being less than 0 for the indicated choice of t1 and t2, since the final x of x times t2 is less than the initial x times t1. So wait, v is less than 0 for the indicated choice of t1 and t2, since the final x times t2. Okay. The average velocity may not tell you the whole story. For example, if you started at x times t1 and at t1 ended up at point C with the same coordinate, the average velocity would be 0, which is the average you would get if the particle had never moved. The average acceleration, a, involves a similar difference of velocities. So a equals v times t1 minus v times t2 over t2 minus t1. Now, for an important concept, the velocity at a given time, or instantaneous velocity, that's a fun little paradoxical statement, shows some particle moving a distance of delta x between times t and t plus delta t. The average velocity in the interval is delta x over delta t. What you want is the velocity at time t. We have an intuitive notion of velocity right now. When you're driving the car, if the needle says 60 miles per hour, that's your velocity at that instant. I mean, there's no such thing as instantaneous velocity, but it's really more of a, what would it be, like the best approximate constant at that moment. But
It's velocity where delta t equals 0. It's a sample.
yes,
It's
I
at
just-
one point in time.
yeah, no, I understand what they're saying. I just like to clarify that it's technically no such thing as specific, velocity without time. The velocity seems to involve two different times in its very definition. Oh, he's saying it right now. The initial time and the final time. We want to talk about the velocity right now. That is obtained by by examining position now and position slightly later, and taking the ratio of the change in position and the time elapsed between the two events. While bringing the 2 points closer and closer in time. We see the figure that when we do this, delta x approaches 0 and at delta t approaches 0, but the ratio becomes tangent of the angle theta shown in figure 1.1. Thus, the velocity at the instant t is v of t is delta of t approaching 0, or the limit of delta t approaching 0. So delta x over delta t equals the derivative of t, or dx over dt. Once you take the derivative, you can take any number of derivatives. Once you take one derivative, you can take any number of derivatives. The derivative of the velocity is the acceleration, and we write it as a second derivative of position. So a of t would equal dv over dt, which would equal d squared x over dt squared. You are supposed to know the derivatives of simple functions like x of t equals t to the power of n times dx over dt equals n t to the n minus 1. So just showing essentially the bax equals bax b minus 1 or whatever it is. Yeah, ax.
That's just showing you those two expressions, x of t equals t to the n and dx dt equals n t to the n minus 1. Those are two different things. It's not multiplying them together.
Isn't that just showing how to take a derivative of a polynomial?
Yeah, the derivative of t to the n is n times t to the n minus 1.
Yes, there you go. So, as well as derivatives of sines, cosines, logarithms, and exponentials. If you don't know them, you should fix that weakness before proceeding. Motion. So, popcorn to the ether. Who wants to read?
You.
Cool.
I got you. All right. So motion at constant acceleration. We are now going to focus on problems. You can't hear my fan blowing or anything? Let me know in the chat as well if it's picking it up on
No, you're
OBS.
good.
Okay, cool. It's so hot tonight. It's unbelievable. All right. Okay. We are now going to focus on problems in which the acceleration a of t is just a constant denoted by a with no time argument. This is not the most general motion, but a very relevant one when when things fall near the surface of the Earth, they have the same acceleration, a equals minus 9.8 meters per second squared equals little g. If I tell you that a particle has a constant acceleration a, and you tell me what can you tell me what the position x of t is? Your job is to guess the function x of t whose second derivative is a. This is called integration, which is the opposite of differentiation. Integration is not an algorithmic process like differentiation. Yep. Differentiation, though it is governed by many rules that allow us to map the given problem into others with a known solution. If I give you a function, you know how to take the derivative. Change the independent variable, find the change in the function, divide by the change in the independent variable, take the ratio as all changes approach 0. The opposite has to be done here. The way that we do that is we guess, and such guessing has to be done on the 300 and such guessing has been going on for 300 years, and we have become very good at it. The successful guesses are published in the table of integrals. I have a copy of such a table at home, at work, and even in my car in case there's a breakdown. What a nerd. So let me guess aloud. I want to find a function that reduces to a number a when I take two derivatives. I know that each time I take a derivative, I lose the power of t, and at the end, or in the end, I don't want any powers of t. It's clear that I have to start with a function that looks like t squared. Well, unfortunately, we know t squared is not the right answer because it's the second derivative is 2, while I want to get a. So I multiply the original guess 1/2 times a, and I know that x of t equals 1/2 times a times t squared, and that will be the second derivative of a.
But real quick, do you get what he's saying there?
No, not at all.
Yeah. So like, okay, t squared. The first derivative of that is 2t. The second derivative is 2. He's like, but we don't want to get 2 because 2 is a constant. We want to get a, right? So what do we change this function by in order to get a instead of 2? He's like, well, instead of taking t squared, we take 1/2 a t squared, because the first derivative of that is just going to be at, and the second derivative of that is going to be a. That's how we end up with a as the second derivative. So this is how we created the equation x of t equals 1/2 at squared. And then when we test it, it works.
I always wondered where they got the 1/2 from, because I started seeing that when I was looking into the Compton thing. So like the classical derivation for momentum is what was it? It was like 1/2 times mv or mp or whatever, or mv, something like that. They did something like that. I was wondering how they got that.
Right. There's more terms.
So yeah, so it's in relation to they if that's a constant, then to make it a derivative of it, they break down the first thing that they want to know and then like multiply it by the squared.
They're turning the constant into a variable so that it doesn't get washed out as the second derivative, right?
Yeah, and he's gonna go as you scroll further down. He's gonna go into like, okay, we got the first term. Now, how do we get the second term, and so on? Because every time that you take a derivative, you lose a term. So they do this process. This process he just did for 1/2 a. They also do that process for every other term in order to figure out what it needs to be.
Okay,
Yo, thanks, Piezo.
thank you.
No worries.
This certainly describes a particle with acceleration a, but is this the most general answer? You you all know that it is just one of many. For example, I can add this one to some number, say 96, and the answer will still have the property that if you take two derivatives, you will get the same acceleration. Now 96 is a typical constant. So I'm going to give you the same c, so I'm going to give the name c to that constant. If we know from basic calculus that finding a function with the given derivative, you can always add a constant to any one answer to get another answer. But if you only fix the second derivative, you can also add anything with 1 power of t in it, because of the extra part will get wiped out when you take two derivatives. If you fixed only the third derivative of the function, you could also add something quadratic in t without changing the outcome. So the most general expression of a position of a particle with a constant acceleration a is x of t equals 1/2 times a times t squared plus b times t plus c, where b, like c, is a constant, where b, like c, is a constant that can be anything. Remember that x of t in the figure describes a particle going from side to side. So you could describe that particle. You can also describe it going up and down. If you do it, I would like to call that vertical coordinate x or y of t. And then you have to realize that in calculus, the symbols that you call x and y are arbitrary. If you use the second derivative of y to be a, then the answer is equation 1.6, which is y of t equals 1/2 times t squared plus b times t equals c. Let me go back now with equation 1.5. This is true mathematically. You can add b times t plus c as we did, but then you have to ask yourself, what am I doing as a physicist when I add these two terms? What am I supposed to do with b and c? What value should I pick? Simply knowing that the particle has an acceleration of a is not enough to tell you where the particle will be. Take the case of a particle falling under gravity acceleration of minus g. Then you would have an equation that looks like y of t equals minus 1/2 times g times t squared plus bt plus c. The formula describes every object falling under gravity, and each has its own history. What's different between one object and another object is its initial height. So y0 is what is it when there's three equal signs? Is that approximately or what?
Is equivalent to.
Oh, equivalent to y sub 0. And the initial velocity v0 is equivalent to v sub 0. That's what these numbers b and c are going to tell us. To find c in equation 1.7, put t equals 0 on the right and the initial height of y sub 0 on the left, and you'll have y sub 0 equals 0 plus c, which tells us that c is just the initial coordinate. Feeding this into equation 1.7, we obtain y of t equals minus 1/2 times g times t squared plus b times t time plus y sub 0. To use the information, the initial velocity, or to use the information on the initial velocity, let us find the velocity associated with this trajectory with equation 1.110, where it's v of t equals dy over dt equals minus g times t plus b, and compare it on both sides at t0. V sub 0 equals b. That's nu sub 0, actually. So anyway, thus b is the initial velocity. Trading b for c, you now have v sub 0 and y sub 0, which makes their physical significance more transparent. We now write the equation as in the form of 1.12. And likewise for the trajectory x of t, when the acceleration is a constant a, the answer with specific initial position x sub 0 is the initial velocity nu sub 0 is equation 1.13. So here we have that old equation. In every situation where the body has an acceleration a, the location has to have this form. So when I throw a candy at you and you catch it, you are mentally estimating the initial position and the velocity and computing the trajectory and intercepting it with your hands. The candy moves in three spatial dimensions, but the idea is the same. Now, there are one other celebrated formula that relates to v of t. And the nu of t, the final velocity at some time to the initial velocity nu sub 0 and the distance traveled with no reference to time. The trick is to eliminate time from equation 1.3. Let us rewrite this as shown in equation 1.14. Upon taking the time derivative of both sides, we get equation 1.15, and then which may be solved for t, which looks like equation 1.16, where we have t equals v of t minus nu, God damn it, I keep confusing nu and v. Anyway, nu sub 0 over a, which gives us equation 1.17 and 1.18, which are usually written as nu squared equals nu squared sub 0 equals 2a x minus x sub 0, where nu and x are assumed to be the values of some common generic time, t. All right, popcorn.
Yo, did anyone notice that they're just playing with derivatives of the kinematic equivalents for g? right?
That's all they ever do, isn't it?
Like so this is h equals 1/2 at squared plus vt, all in different forms in derivative form of certain points, right? Or am I missing that? That's what this is doing. It started with g, and then it took the kinematic equivalent of g, which I use all the time, right? And was like, and then it gave it functions, derivatives, and what was the opposite of derivative?
Integrals.
Yep. So like it's doing integrals and derivatives of the kinematic derivation of g, gravitational constant. How about that, boys? That's how it starts, huh?
How it
Wow.
starts. All right. So popcorn, Pizio, Travis, anyone? Either of you two?
I can pick it back up if no one else wants to.
Yeah, I mean, I can jump in here.
Yeah.
Okay. I was watching your screen, so I have to find yours where we left off here.
You're good. We're at 1.5 sample problem.
Oh, okay. Okay. All right, I'm not. Just bear with me here, boys. All right, so
You're good, bro.
we will work through one standard problem to convince ourselves that we know how to apply these formulas and predict the future given the present. Figure 1.2 shows a building of a height of y sub-0 equals 15m. I'm going to throw a rock with an initial velocity v0 equals 10 miles, or let's see, 10 meters a second from the top. Notice I am measuring y from the ground. The rock is going to go up to point T and come down as shown in figure 1.2. You can ask me any question you want about this rock and I can give you the answer. You can ask me where it will be 9 seconds from now, how fast will it be moving 8 seconds from now, and so on. All I need are the two initial conditions, y of 0 and v of 0, that are given. To make life simple, I will use a equals negative g equals negative 10 ms squared. The position yt is known for all future times. Y equals 15 plus t minus 5t squared. Of course, you must be a little careful when you use this result. Say you put t equal to 10,000 years. What are you going to get? You're going to find y is some huge negative number. That reasoning is flawed because you cannot use the formula once the rock hits the ground. And the fundamental premise that a equals negative 10 ms negative 2 becomes invalid. Now, if you had dug a hole of depth d where the rock was going to land, y could go down to negative d. The moral is that when applying a formula, you must bear in mind the terms under which it was derived. Got a little figure here. If you want to know the velocity at any time, just take the derivative of equation 1.20. Vt equals 10 minus 10t. Let me pick a few more trivial questions. What is the height y max of the turning point t in the figure? Equation 1.20 tells you y if you know t, but we don't know the time t when it turns around. So you have to put in something else that you know, which is that the highest point occurs when it's neither going up nor coming down. So at the highest point, Vt equals 0 from equation 1.21, 0 equals 10 minus 10t, which means t equals 1s. So we know that it will go go for 1 second, and then turn around and come back. Now we can find y max. Y max equals yt equals y1 equals 15 plus 10 minus 5 equals 20m. When does it hit the ground? That is the same as asking when y equals 0, which is our origin. When y equals 0, 0 equals 15 plus 10t minus 5t squared. The solutions to this quadratic equation are t equal 3s or t equals negative 1s. Why is it giving me a second solution? Can t be negative? First of all, negative times should not bother anybody. T minus 0 or t equals 0 is when I set the clock to 0 and I measure time forward. But yesterday would be t equals negative 1 today, right? So we don't have any trouble with negative time. It is like the year 300 BC. The point is that this equation does not know that I went to a building and launched a rock or anything. What does it know? It knows that this particle had a height of y equals 15m and velocity v equals 10 ms at time t equals 0. And it is falling under gravity with an acceleration of negative 10 ms to the negative 2. That's all it knows. If that's all it knows, then in that scenario, there is no building or anything else. It continues a trajectory both forward in time and backward in time. And it says that 1 second before I set my clock to 0, this particle would have been on the ground. What it means is that if you had released a rock to 0 at y equals 0 on the ground 1 second before I did with a certain speed that we can calculate, v to the negative 1 equals ms from equation 1.21. Your rock would have ended up at the top of the building when I began my experiment with the same height, y equals 15m, and velocity v0 equals 10 ms. So sometimes the extra solution is very interesting, and you should always listen to the mathematics when you get extra solutions. When Paul Dirac was looking for the energy of a particle in relativistic quantum mechanics, he found that the energy E was connected to its momentum, P, mass M, and velocity of light, C, by E squared equals P squared, C times C squared plus M squared times C cubed, or whatever.
To the fourth.
Yeah, that. In accord with the relation we encounter in relativity. Now, this quadratic equation has two solutions. E equals plus or minus the root of c squared, p squared plus m squared, and c to the fourth power. You may be tempted to keep the plus sign because you know energy is not going to be negative. The particles moving, it's got some energy. Well, let me start that over. You may be tempted to keep the plus sign because you know energy is not going to be negative. The particles moving, it's got some energy, and that's it. This is correct in classical mechanics, but in quantum mechanics, the mathematicians told Dirac, you cannot ignore the negative energy solution in quantum theory. The mathematics tell you it is there. It turns out the second solution with negative energy was telling us that if there are particles, then there must be antiparticles. And the negative energy particles, when
No
properly,
way. That's where it came from. That's insane.
Counter space particles, bro, but it's not particles. It's just
Dude,
wave functions
the
in reality.
math is telling us it's there. You have to incorporate it, Dirac. Get out of town,
Astounding.
bro. No
And hey-
snap, they did that.
And my brothers, I'm really rusty. I haven't studied math in a long time, so sorry.
You're straight, bro. You're straight.
I just wanted to, yeah, man. I just really want to try to understand some of these concepts. Okay, so when properly interpreted, describes antiparticles of positive energy. So the equations are very smart. Yes, indeed. When you find,
If you say so.
Yeah, we'll go ahead and make that super not.
Pink. There you go. Yep.
Sorry, go ahead and continue, please.
when you find some laws in mathematical form, you have to follow the. Sorry, I got a frog in my throat. You have to follow the mathematical consequences. You have no choice. Here was Dirac, who, am I saying that right? Dirac?
Yeah. Yep.
Dirac, okay. Who was not looking for antiparticles.
It's actually a silent D.
Okay. Well, fuck that guy. His name's Dirac. He was trying to describe electrons, but the theory said there are two roots to the quadratic equation, and the second root is mathematically significant as the first one. And trying to accommodate and interpret Dirac was led to the positron, the electron's antiparticle. Returning to our problem, if you were only asking for the maximum height y max and not the time when it got there, there is a shortcut using v squared equals v sub 0 to the second power plus 2a y minus y sub 0. That's sub 0. That's kind of cool.
Yep.
I like that math term. Is that right? Did I say that right?
Yep.
Yeah.
Wow. Man, I'm impressed with my. Anyhow, pattern recognition. Using v equals 0. V sub 0 equals 10 ms and a equals negative 10 ms to the negative 2. We find y max minus y sub 0 equals 5m. That is the rock reached at a maximum height of 20 m from the ground. You can find the speed.
The little m here is going to be meters, and then when you see this, it's meters per second squared. So
or meters per second to the negative 2.
Meters per
that particular one.
Okay.
Meters per squared second. So we're talking about velocities and accelerations here, guy.
Yeah, and these are distances. Okay, gotcha. That is rock means height of 20 meters from the ground. You can find the speed when it hits the ground. Y equals 0 using v squared equals 10 squared plus 2. Negative 10. That equals 400, which means v equals plus or minus 20 meters a second. Okay, so the route we should take for when it hits the ground is, of course, negative 20 meters a second, as mentioned earlier. The other route, plus 20 meters a second, is the speed with which it should have been launched upward from y equals 0 at t equals negative 1 to follow the dotted trajectory in the figure. Do you guys want me to keep going, or?
You can pass.
Are we going to do? Okay, yeah, I'll keep going here. All right, so I want to derive equation 1.19. V squared equals v sub 02 equals 2a times x minus x sub 0. In another way that illustrates the judicious use of calculus. Start with dv over dt equals a, and multiply both sides v and right. V equals dx over dt in the right hand side. V over dv dt equals a over dx over dt.
So Piezo, right there, they're just real quick. Piezo, right there, all they're doing is pulling out one of the derivatives for the chain rule, right?
Is he deafened?
He is actually.
Yeah.
But I believe that's all they're doing is just pulling out one of the derivatives so that they can do a double double derivative.
A double D?
Build double D. So yeah,
The
go ahead.
derivative of velocity is acceleration.
What's that, Scott?
I was just saying that's really common. The dv dt equals acceleration. I mean, they like in this classical. I mean, I don't know about that chain equation you were talking about. I mean, just dv dt equals a. I mean, they're constantly taking the derivative of velocity to get acceleration. I mean, they do that. You know. So anyway, that's all I was clarifying. It's pretty. It's just velocity or acceleration. I mean, dv/dt is equal to a. They use that constantly. Sorry, I don't know if that's unclear, but
No, you're good. So they're
there's
getting
no
the
chain equation. What's that?
nothing. You're good.
I think you're right.
Yeah, I mean, it's just by definition, the derivative of velocity with respect to time gives you acceleration. Which is why it's that meters per second squared. You have 2 times under the man, it's been a long time, but you know, in the bottom of the fraction.
The denominator.
Yeah, the denominator. Thank you. So acceleration is always a meter. It's always like a distance per time, whereas velocity is always, you know, just distance over time.
Oh, got you. Gotcha.
Although this is mostly semantic. I mean, we're not really in any meat or anything here, but
yeah.
But we're about to see the second time he stresses careful interpretation of what's going on in order to arrive where he wants you to be.
Huh.
Oh, is he leading us down a path of darkness, Stone?
Well,
Are we about to take
No
never-ending
spoilers.
differentials?
It does so far kind of just look like we're taking an acceleration function, right? Seems to be all we're really doing. You're right.
Deriving it from the old veloc.
Yeah.
Well, see, he's got dv, like in that one equation, he's got dv dt, so that is a. So it's va, and then on the right hand side, he's got a equals dx dt. So that's v, because dx is the distance, the change in the distance or the change in time. You know. So I don't know where he's headed with that, but like if you're comfortable with those differential things, I mean that's a totally straightforward. It's just like you know, v times acceleration equals acceleration times v.
Nice.
all right, I'll keep going here. So now I'm going to do something that is viewed with suspicion, which is just to cancel the dt on both sides. Although I agree that you're not supposed to cancel that d and the dy over dx. Canceling the dt on both sides gives valid results if interpreted carefully. Okay. Doing so,
You know,
here gives us, yep.
well, I just thought I'd pipe up because I don't know if this is clear to everyone. You know, when he says that about not canceling the dy dx, it's because those d's aren't terms in a normal way. Otherwise, you could cancel them, but it means differential. So, I mean, that would be ridiculous. I mean, of course, you can't do that. But
we're gonna do it anyway.
Yeah, it's
Well,
it's
I guess
not
if
to be
you-
confused with terms. It's a notation specifically when you do d over d like that.
Yeah. But then canceling the dt on both sides gives valid results. Yeah, that seems a little fishy because it seems like he's treating the differential as if it's a regular term there. Anyway, let's see where he goes.
All right. Doing so here gives us v dv equals a dx. This equation tells us that in an infinitesimal time interval, t plus dt, the variables v and x change by dv and dx. And these changes are related as above in the limit dx, dv, dt to 0. Now, the limit of dx to 0 or dv to 0 as compared to their ratio is of course trivial. And equation 1.33 reduces to 0 equals 0. However, the way we interpret the use of equation 1.33 is as follows. Suppose in the finite time interval t1, t2, the variable v changes from v1 to v2, and x changes from x1 to x2. Let us divide the interval t1, t2 into a very large number n of equal intervals of width dt, and let dx and dv be the changes in x and v in the interval t plus dt. The relation between these changes is given in equation 1.33. If we sum up the n changes on both sides of equation 1.33 as n to infinity.
Approaches infinity.
Okay, it's approaches is the arrow?
Yep.
Okay, gotcha. N approaches infinity. The sums coverage to non-trivial limits, namely the corresponding integrals.
So what he just basically described is how you take limits. So scroll back up a little bit real quick. When he's talking about, so the equation tells us that in an infinitesimal time interval. So you're going to keep going smaller and smaller and smaller. When I was saying earlier, there's no such thing as like an instant velocity. Like you can't take a moment velocity. That's kind of what I was getting at, is this right here, is that really what you're doing is you're approaching from both sides of the tangent of the velocity on the function, and you're going as close as you can. You're taking a chunk of time that is like getting small. You're approaching 0 with the amount of time that you're calculating the velocity at that specific time for. And as you're approaching 0, or you're approaching infinity or 0, depending on how you're taking your limit, as you're approaching, or really you could be approaching any figure, but in any case, as you're approaching, you're going to get to the point where essentially you get to the 0 point, and so that's why you can take derivatives differently from taking a limit, because you can just kind of skip some of the terms that end up canceling out. But so when you take a derivative, you take a derivative, you can take an antiderivative, and then you can take, what he's going to describe now is how you can calculate an integral area, taking these these best approximations of a instant velocity at 2 points on a velocity or an acceleration function.
Yeah, that's the trick of all this, I would say. I mean, the one thing is to sort of optimize that one moment where you trend to 0, and that's where the math it extracts that rate of change right at that hypothetical moment.
So this next equation, when he's showing the integral of v1 going to v2, vdv equals a times the integral of x1 going to x2 times dx. You'd be calculating the area under your function. You take the derivative of the function at both of those points, and then you calculate the area under those points of your function to get the total distance traveled. So you take your acceleration function, and then you can calculate a very close approximated distance based on those 2 points of the function, essentially, if that makes any sense.
Yeah.
Dude, awesome explanation, Toby. Thanks so much for that, brother.
My pleasure.
Yeah, man.
Hopefully it made sense.
Yeah, dude, it's gonna take time. We're just gonna soak in. This is just cool, man. This is a lot of fun. So appreciate you guys, everyone being here. All right, so thus it must be understood that the two sides of a relation, like equation 1.33, are to be ultimately integrated between some limits to obtain a useful equality. Equation 1.19 follows up upon setting v equals, or v2 equals v1 equals v sub 0 x2 equals x1 equals x0.
So when you have the little numbers like these under the under the other variable, that's
Yeah,
a
yeah,
sub
yeah.
as well. So it'd be
A
sub 1, sub 2. Yep.
Okay, gotcha. Oh, it's like a subset because it's just
Yep.
all
And
like
if it,
It just
Yeah.
gives
you
the
see-
exact. It gives it a number. V is just vague, but like V2 would be like 7, and V1 would be 3, for an example. You know.
okay. Yeah.
Yeah.
Okay, I'm kind of getting it. Yeah,
And it's
yeah.
when it has the sub number, it's making it it's saying it's some concrete value.
Ah, okay. Right on. Righteous. Am I going to keep going here? Does tag in Pizio? Are you up for motion in higher dimensions 2.1 review? We are on page 33.
I'm about to cook, but yeah, I can do it real quick.
Okay.
All right. In the last chapter, we took the simplest case of a point particle moving in the x-axis with constant acceleration. What's the fate of the particle? The answer is that at any time, the location of the particle is given by the following equation. X of t equals x naught plus v naught t plus 1/2 at squared, where x naught and v naught are initial position and velocity. If you took the derivative of this equation, you would get vt equals v naught plus at. You can easily check by taking one more derivative that this particle does indeed have a constant acceleration a. This equation, which gives the velocity of the object at time t, in terms of its initial velocity and acceleration, can be inverted to give t in terms of v. T equals v minus v naught over a. If we feed this into equation 2.1, we obtain the result that makes no reference to time. V squared equals v naught squared plus 2a times delta x, x minus x naught. It is understood v and x correspond to some common time. I showed you in the end how we can use calculus to derive this result. It's important to brush up on your calculus. When a student says, I know calculus, sometimes that means the student knows it, and sometimes that means he or she once met someone who did. One solution for that is to get a copy of a textbook I wrote called Basic Training in Mathematics. It's a little awkward. I don't want to foist my book on you. On the other hand, I don't want to withhold relevant information. If you're going into any science that uses math, you would, chemistry, engineering, or economics, you should find the contents of the book useful. Don't wait for the movie. It's not coming. So vectors in D equals 2. Now the next difficult thing is to consider motion in higher dimensions. Everything moves around in in 3 dimensions. However, I'm going to only use 2 dimensions for most of the time. Whereas the difference between 1 dimension and 2 is very great, the difference between 2 and 3 is not. Or 2 and higher is not. Later we will encounter a few concepts that make sense in D equals 3, but not D is less than 3. String theorists will tell you that actually we need 9 spatial dimensions plus time to describe superstrings, which will be discussed in depth in chapter 3498 of this book.
That was a perfect tone, by the way.
Picture some particle that's traveling in the XY plane, as in figure 2.1. It's not X versus T plot or a Y versus T plot. It's the actual path that the particle traces out on the XY plane. You might say, where's the time? Well, one way to mark time is to imagine the particle carries a clock with it and put markers every second. 4 representative markers at t equals 1, 2, 33, and 34 are shown. Obviously, it's going to be moving much slower between 33 and 34 than between 1 and 2. Now, the kinematics of this particle require a pair of numbers, x and y. It's more convenient to lump these into a single entity called a vector. Now, the simplest context in which one can motivate a vector and the rules for dealing with them is to look at movements in the plane. Let's imagine I went camping and I walked 5 clicks from the base camp on the first day and another 5 clicks on the second day. How far am I from the base camp? Well, you can't answer that. Even if I promise to move only along the x-axis, it's not enough to say I went 5 clicks. I have to tell you whether I went to the right or to the left. So I could be 10 clicks, 0 clicks, or negative 10 clicks from base. If I say not just that I walked 5 kilometers, but specified whether it was plus or minus 5 kilometers, that takes care of all ambiguity in one dimension. Now, this is the plot that he was talking about with 1, 2, 33, and 34 seconds in time. But in d equals 2 in 2 dimensions, the options are not just left and right, but in an infinity of possible directions. For example, on the first day, I could leave the base camp at the origin, move along the arrow labeled A, if you'll scroll down just a little, to arrive at the point. Can you scroll down just a little? To arrive at the point, thank you. To arrive at the point labeled 1 in figure 2.2. The second hike is described by the arrow B, which starts where A ended and brings me to 2. These two arrows are examples of vectors, and I use them here for describing displacement or changes in position. Vectors can be used to describe many other physical quantities, as we will see. A vector is an arrow that's got a beginning and an end. That's why it has like an arrow above the letter to describe the vector. That's vector notation. This is why one says a vector has a magnitude and a direction. The magnitude is how long it is, and the direction is its angle relative to some fixed direction, usually the x-axis.
Sorry, I just want to look at the arrows real quick.
Yeah. When you refer to a vector A in your notes, you're supposed to put a little arrow on top of A like this. He doesn't have the arrow drawn, but in textbooks, vectors are in boldface, A. If you don't put an arrow on top or do not use boldface, you're talking about just the number A. When applied to a vector, bold A stands for its length. From figure 2.2a, we see that there's a very natural quantity you can call vector A plus B. One day I move by vector A, and the next day by vector B. If I want to do it all in one shot, what's the equivalent step I should take from the start? It's obvious that the bottom line of my 2-day trip is object vector C. We'll call that vector A plus B. Now, it does represent the sum in the same sense that if I gave you $4 and then I gave you $5, you have the equivalent of a single payment of $9. Here, we're not talking about a single number, but just a displacement in the plane. And C indeed represents an effective displacement due to A and B. So here's the rule for adding two vectors that comes from a study of displacements. You draw the first one, and at the end of that first one, you begin the second one. And their sum starts at the beginning of the first and ends at the end of the second. You can verify, as illustrated in the figure, that A plus B is the same as B plus A, right? So what are you saying? Like, if you think of it real quick, if you think of like a triangle, if you start at an origin point and you draw an angle out to one side and then an angle out to the other side, you draw two sides of a triangle. You can make the third side of a triangle starting from the start point and ending at the end point, which would be kind of like the hypotenuse. And that hypotenuse is going to be like the vector sum of the first two lines.
Oh, gotcha. That was mad helpful.
So you can verify, as illustrated in the figure, that vector A plus B is the same as vector B plus A, where you draw from B and where you first draw B, and from where B ends, you draw A. You'll end up with the same point, 2, as shown by the sum of the dotted arrows. Now, the next thing I want to do is to define the vector that plays the role of the number 0, which has the property that when you add it to any number, it gives the same number. The vector 0, that I want to call the 0 or null vector, should have the property that when I add it to any vector, I should get the same vector. So you can guess who it is. It's a vector of no length. I can't show you the 0. If you can see it, I'm doing something wrong. Now look at part B of figure 2.2. Can you scroll up real quick? Just to see the right-hand side. Right, he's got A plus A equals 2A. A plus negative A equals 0, right? All right. See the lines on the right side? Yeah.
Yep, got it.
If I draw A, then I add to it another A, I get A plus A. You agree that there's a vector that deserves to be called 2A? It's this guy. A stretched to twice its length. Now, we discovered a notion of multiplying a vector by a number. If you multiply it by 2, then you get a vector that's twice as long in the same direction. So we're going to be able to generalize that. And then we can say if you multiply by 2.6, you get a vector 2.6 times as long, and so on and so forth. So multiplying a vector by a positive number means to stretch it or to shrink it by that factor. Let's keep going. If I want to think of a vector that I call it negative A, what do I expect of it? I expect that if I add negative A to A, I should get a 0, which plays the role of 0 among vectors. So what should I add to A so that I get a null vector? It's clear that you want to add a vector that looks like negative A from that picture above. Because if you go from the start of A to the finish of negative A, you end where you started, and thus you get 0, an invisible 0 vector. So the minus vector is that same positive vector just flipped over in the opposite direction, pointing the opposite way. That's like taking the vector and multiplying it by -1. Once you got that, you can do -7.3 times a vector. You just take the vector, you rescale it to by 7.3, and you flip it over. Multiplying by a vector, or multiplying a vector by a number, is called scalar multiplication. And ordinary numbers are just called scalars. Like that's a number without a direction, just any general number. You think of a number, that's called a scalar. You can do more complicated things. You can take one vector, multiply it by one scalar, take another vector, multiply that by another scalar, and then add the two of them together. We know what all those operations mean now. You don't have to memorize the rules for all this. The only rule is do what comes naturally. Do what you normally do with ordinary numbers. Just remember the little line on the top, or like the bold print, is a vector. So that's just a number plus a direction. All right. Somebody else want to?
Yo, thanks, Pizio. Much appreciated.
No words. Real quick though, before I go on, the way that like adding vectors together to get the sum works, I use the triangle to describe it. You can't obviously just add up two numbers in two different directions and expect them to add up to a third number just normally. You have to actually multiply by an angle, because that angle is going to like give like the basically like the percentage, right, offset of, like if I'm moving in a straight line and I say, and this is the x-axis, I move 100 meters along the x-axis in a straight line, I just moved 100 meters in the x-axis. But if I now like aim myself 45 degrees to the right and I move 100 meters, well, I didn't really move 100 meters in the x-axis. I moved 100 meters like total, like in absolute space, I moved 100 meters, but along the x-axis, I only ended up moving 50 meters.
Because you're just going as far as the slope value will take you, right?
Yeah, so it's measured along an axis, right? So like if I can move 100 meters in the x-axis and I moved 100 meters in the x-axis, I can now angle myself 45 degrees offset to the right or to the left. If I move 100 meters in that 45 degree offset, in total I did move 100 meters, but with respect to the x-axis, I only moved 50 meters. Because
makes sense.
When measured along the x-axis, right, it's only the forward motion. Like all that other sideways motion is like not represented in that axis. So when you do vector sums in like the xy plane he's talking about, it's kind of like drawing a bunch of triangles. You got to take the angles into account.
Cool. Anyone else want to read? How far did we want to go?
I think we can see how long this one is. I wanted to at least get to Newton before we tapped out. Yeah, we got quite a ways to go.
He's about to show He's about to show. I can do this part real quick if you want me to do he's going to do the sign thing. You want to burn through it real fast?
I mean, if you're trying to burn, bro, I'm not going to stop you.
All right, let's go 2.3 real quick.
All right, send it.
All right, let's go back to the same XY plane. Let me introduce two very special vectors. They're called unit vectors, I and J. They point along the X and Y axes, and they're of the unit length as shown in figure 2.3. If I had a third axis perpendicular to the page, I'd draw a K, but we don't need it yet. I claim I can write any vector you give me as a number a sub x times I, plus a number a sub y times j. So he's representing the x-axis as I and the y-axis as j. There's nothing you can throw at me that lies in the plane that I cannot describe as some multiple of I plus some multiple of j. It's intuitively clear, but I'll just prove it beyond any doubt. So here's some vector A. It's clear from the figure that it's the sum of the dotted horizontal vector and the dotted vertical vector by the rules of vector addition. The horizontal part, parallel to I, has to be a multiple of I. We know that because we can stretch I by whatever factor we like. Call that factor a sub x, which happens to be positive in this example. It's called the x component of A, or the projection of A along I, or along the x-axis. Now the vertical part is likewise j times a sub y, where a sub y is the y component of A, or the projection of A along j, or along the y-axis.
Therefore, to screw up your variables. I'm sorry, Pizzo. I have a fundamental pedagogical problem with this paragraph. If you scroll down a bit and take a look at the diagram, 2.3, you can see that he's drawing out A diagonally at some angle theta there. And the angle doesn't matter. The point is that he's showing I and j close to the 0, 0. You know what I mean? And he's suggesting that the dotted lines represent two component quantities of the total vector of A, the horizontal quantity and the vertical quantity. The quantity that goes along axis I and the quantity that goes as far as axis J, right? But he then goes down outside of those with the parentheses and puts it A sub X and A sub Y instead of A sub I and A sub J. Do you guys follow me on this idiocy?
Are you talking about the notation? Yeah, like how he's
Yes,
using
this is a
two separate-
pedagogical fail right here. Cognitive separation between associative cause, mathematically speaking. This kind of shit in the mainstream drives me crazy when I see dumb shit like that. I mean, okay, this guy's doing really great in the calculus department, but come on. Does nobody else see this? It just makes it so
Could you clarify?
1 degree less intuitive. You know what I mean?
Yeah, I think he's
graph
gonna
system
do a theta angle for I and J, right? Isn't he gonna do that?
It's that A sub X should actually read A sub I.
Yeah, I know what you're saying.
If
But
he's calling the axes I and J, then the subs should be I and J to represent them. It's simple
Yeah.
intuitive connection of the values, right? Fuck me. Anyways, go ahead. Thank you. I'll get off my soapbox now.
That certainly
Okay.
seems like a more intuitive convention. I would agree with that.
Yeah, let me see what he's gonna do in a second. I need to see the below equations below this one because I feel like he's gonna use I and J as just constants that are able to be multiplied by A sub X and A sub Y to give the relevant like percentage ratios to make the overall A correct. But I don't know what the equations below look. Can you scroll down a little bit?
It's great. I was just talking about the nomenclature and that he's screwing the pooch here.
No, but
Go
I
ahead,
think,
guys, let her
if
rip.
I may add a little bit of a clarification, I think it's a scalar number, so you multiply that one later. That's where you make a distinction. X and Y are like specific numbers. If that
Can you
makes
scroll
sense.
down a little more? Can you scroll down a little more?
But there are specific
yeah,
numbers
yeah,
that are associated with those axes,
okay.
right? That's all
Yeah,
I'm
yeah,
saying.
Yeah. Okay. Scroll back up. We're good. We're good. Yeah. So if you notice, I and J are bolded. So I and J are like vectors, and A sub X and A sub Y are constants, are scalars. And he defines A sub X and A sub Y as A cosine theta and A sine theta, right? Just doing the triangle math. So yeah, I see what he's saying. When we write this like in physics, the way that they do like vector sums, like you got A with a little line above it. A is going to be like there's like also like a little caret, the caret symbol, like a little tiny arrow, little hat or whatever. It's going to be like I hat plus J hat plus K hat equals, a vector in the 3D space. If it's 2D space, it's going to be A equals I hat plus J hat. Yeah, the only reason that the I and J are even useful, I agree with Stone here, is that it enables you to have a separate notation where you just represent this whole everything below, like AX equals A cosine theta and all this stuff. You can just represent it all as one letter. So that's why he sets it up. I think that's probably why he's setting it up now, because later you're able to just do like I hat plus J hat. And we've already defined.
Okay, I will suspend offense. Let's see how far he gets.
Okay, may I say something?
Yes.
Absolutely.
Okay. It's a convention or standard notation to use the unit vector it points in the positive direction of the x-axis to be denoted as the boldface I. The same thing for J, it's convention, standard. You can change it if you want, it's just a notation. J is the unit vector that points in the y-axis, positive direction. And then later when we get to K, boldface K would be the unit vector that points in the positive z direction. So this is a convention. I mean, if you use this, everyone will understand it because it's what's commonly used. But you all make good points, but I just wanted to say this to help clarify.
Yeah, it's useful for
It's
making
almost like
shorthand later.
It
seems
sounds like an
almost in the
agreed
vectors-
upon point of clarification where they've deliberately caused confusion. I understand that you're separating the convention between the axis and the vector component. I get that. But it just doesn't strike me as intuitive. Why do we need the convention? Why? Because one is full character and one is subscript. That should be the difference. You know what I mean? That the only one needed.
Got it.
I think for vector math, am I on?
Yep.
Can you even hear me?
You're good.
Oh, yeah. I'm just recalling, I'm not entirely sure, but I think that I and J and what the other person was saying too, those are like the unit vectors, I in the X direction and J in the Y direction.
Mhm.
So seeing what you're saying, Stone, but I kind of think in this, like for it's known you're on the X and Y axis because you're using the I and J representative unit vector,
Okay.
I being
So
X and J being
let's clarify the full slate of nomenclature there. If the I, J, and K are the positive vector values, what are the negative ones that are also X, Y, and Z?
It'd
I
be
think
negative
that-
I, negative J, negative K.
Yeah.
They would be
Negative
well,
I,
first-
negative J, negative K?
Right.
Yeah.
Yes, they would be
Well,
that.
then
Those
you
would
could
be-
still use negative X, negative Y, negative Z. It just really isn't
Yeah.
necessary.
Okay.
That's just crazy. Call me
I-
crazy, but
No,
that's
I'm
just
not
the
gonna
way I
call
see
you
it
the
in terms of
same.
simplification
Not gonna
of
call-
concept.
I'm really reluctant to say this, but if Stone, if you wanted to represent a unit vector in the X direction, right here in the book, it's boldface I. What would you think about using a boldface numeric 1, so 1, bold, sub X instead of I? What would you think about that? Uh-oh, I shouldn't have done
I don't
this.
know.
So that would mean it's the boldface would mean it's a vector. The fact that it's the numeral 1 means it's a unit vector, and then the subscript X would mean this is a unit vector in the X direction.
Well, in this case, representative speaking, then you're going to have vector A equals 1 sub X, A sub X,
Yes.
plus 2 sub X, A sub Y.
No. 1 means it's a unit vector. Boldface 1 sub Y. J is replaced by that.
1 sub
Boldface-
X and 1 sub Y. I
Yeah,
see.
1 sub Y. Yeah.
Well, I guess you're numbering your axes instead of lettering your axes. But the thing is that you're using the same number system that you're using to arrange your mathematics and resolve with. So I'm not sure that's all the clearer in terms.
Okay.
Yes,
Well,
that is if you're going to number your axes. But again, we argued to beginning the importance of convention, and I'm all right with Cartesian X, Y, and Z. But I think we should stick to them if we're going to stick to them. That's kind of
Right.
what I
Oh,
would
yeah,
say.
that's extremely important. If you have a convention,
Yeah.
you got to stick with it. Otherwise, if you don't stick with your convention, you're just going to go in the direction of confusion.
Yeah.
Okay, so maybe I haven't been exposed to this convention enough. Maybe
I
that's
think
what
that
it
the
takes.
way they do it is because I, J, and K are the vector quantities, and X, Y, and Z are the scalar quantities. So they make a distinction between the vector and scalar quantities. So that I relates to X, J relates to Y, K relates to Z. But if you're talking about the vector, you want to represent it in I. If you're talking about the scalar, you represent an X. That way, you're able to do both vector and scalar math side by side or at the same time.
Well, yeah, the
without mixing
scalar
them up.
and
I think that's
the
it.
its components.
And also
yeah.
the boldface I and J helps distinguish that it's vector too.
Right.
Yeah,
But if you were to write like
okay,
bold
okay,
X, if you were to
okay.
write like bold X and then not bold X, it would get too confusing. So it's like that's why they do the I instead of the X, I think.
Well, it's full scale letter to not subscript. You know, it's
Flat
already
earthers-
geometrically separated in the impression you get in its placement.
They could also say I times
That's
X
okay.
plus J times Y. They could do that, but I mean it's they do A sub X because they're denoting like the X component of A rather than just X itself. There's different ways you could do the convention.
Oh,
like
I
this
get
was
why. Yeah.
Yeah. There's different ways you
Yeah.
can do
Okay.
it.
Flat
It just
earthers
struck
are
me as less than
so
completely intuitive.
flat earthers are
picky, aren't we?
so dumb that they sit around and argue about vector math notation with
And pedagogical approach. Yeah.
deep conversations about approaches to vector math notation.
Yeah, what-
meticulous and thorough in their free time, no less, to
Yeah.
analyze these things. I mean, yeah,
Well,
that's
For sure.
different
when
crowd.
when I first learned about like, you know, doing all this in physics, I thought it was kind of counterintuitive at first too to do I, J, and K because I'm like, why would they not just use X, Y, and Z? I don't get it. But like later, when you start multiplying vectors and scalars together, it makes it easier later down the road because then you don't use the same letters all the time to represent separate quantities. Since you already know that I, J, and K relate to X, Y, and
But
Z.
it's their separate physical position on the line as well that doesn't really make that as muddy as you think. That's all I'm trying to point out, I guess.
I gotcha.
You know what I mean?
Yeah, you
One's
could
full
totally do
script,
another
one is sub.
notation.
Yeah.
Yeah.
Anyways, let's keep this ball rolling. We've got
Yeah. So vector A equals vector I times a sub x plus vector j times a sub y. Now we can refer to the pair I and j in terms of which any vector can be expressed as basis vectors or as the basis. If you gave me a particular vector A as an arrow of some length a and orientation theta relative to the x-axis, what do I use for a sub x and a sub y? You can see from trig that a sub x equals a cosine theta and a sub y equals a sine theta. That you can use your little SOHCAHTOA acronym to help remember which one to use. Conversely, given the components, the length and angle are a equals the square root of a sub x squared plus a sub y squared. Realize this is just the base and height of the triangle getting the hypotenuse, right? Or theta equals arctangent of a sub y over a sub x. Equations 2.6 to 2.9 will be invoked often, so please commit them to memory. If you give me a pair of numbers, a sub x and a sub y, that's as good as giving me this arrow, because I can find the length of the arrow by Pythagoras' theorem, and I can find the orientation from tangent theta equals a sub y over a sub x. You have the option of either working with the two components of a or with the arrow. In practice, most of the time we work with these two numbers. In particular, if we were describing a particle whose location is the positive vector r, then we write it in terms of its components as r equals ix plus jy. The changes in r are the displacement vectors, and examples are a and b in figure 2.2 that describe the two hikes. Now, I've not given you any other example of vectors besides the displacement one, but at the moment we'll define a vector to be any object that looks like some multiple of I plus some multiple of j. If I tell you to add two vectors a and b, you've got two options. You can draw the arrow corresponding to A and attach the end of it to an arrow corresponding to B and add them together, as in figure 2.2. But you can also do the bookkeeping without drawing any pictures as follows. Vector A plus vector B equals I, A sub x, plus J, A sub y, plus I, B sub x, plus J, B sub y, equals I times parentheses A sub x plus B sub x, plus J, parentheses A sub y plus B sub y. So that the sum C is a vector with components x component, a sub x plus b sub x, and y component, a sub y plus b sub y. It's just a fancy way of grouping all the terms together. You get all the x terms grouped to the I, all the y terms grouped to the j. So in the above...
I just, to Stone's point earlier about the, clarity of the... It almost seems like in parentheses there, they should have an I, ax plus bx, comma, j, ay plus by, boldface I and boldface j, just to indicate that those are still vectors. You follow what I'm saying?
Yeah, so the whole... The C, if you scroll up just a little bit,
where it says C is the vector with components, and then in parentheses, it seems like they should have a boldface I.
Back down. You're right there. If you compare equation 2.10 and equation 2.12, you'll see that they're the same thing. It's just breaking.
I'm meaning actually down below 2 point. This is also a really minor point. I was just to Stone's thing about clarity earlier. It's under equation 212. It says so that the sum C is a vector with components, and then it seems to me like they should have a boldface I to indicate that those 2 points are still vectors. So an I, ax plus bx, comma j, bold j, ay plus by. Did you see what I mean?
Well, you don't need the
quickly too.
Yeah, you don't need the vector there.
They
that part
appear
of the
bolded.
components. Yeah,
You mean to indicate you don't need the vector in the to
not
show
in the
that the sum
parenthetical
C-
expression, not in the not in the
No?
parentheses.
Well, it seems like it would
the
make it clearer to have it, to have the IJ. But anywho,
In the above, I've used the fact that vectors can be added in any order. So I grouped the things involving just I and likewise j. Then I argued that since I, a sub x, and I, b sub x, are both vectors along I, that their sum is a vector of length a sub x plus b sub x, also along I. I did the same for j. So in summary, if vector a plus vector b equals vector c, then c sub x equals the sum of a sub x and b sub x, and c sub y equals the sum of a sub y and b sub y. So it's literally just breaking down like scalar quantities along a particular direction, right, in terms of the directional components of all the scalars added together. So it creates one total vector sum. So, vector equals all the, if you have a 3-axis vector, then your vector along, like your total is going to be, the sum of all of the components in that axis.
It's the distributive property.
Yeah. And which can be summarized as follows. To add two vectors, add their respective components. An important result is that vector A equals vector B is only possible if the both components of each are equal, such as a sub x equals b sub x and a sub y equals b sub y. This means that the vectors are equal. You can't have two vectors equal without having exactly the same x and y components. If two arrows are equal, one cannot be longer in the x direction and correspondingly shorter in the y direction. Everything actually has to match completely in each axis. The vector equation, vector A equals vector B, is actually
Hold on.
shorthand for two separate equations. A sub x equals b sub x and a sub y equals b sub y. All right. Are you guys picking up what he's putting down about, vectors just being a sum of different components put together?
Can we get the Pizio explanation?
Give us the PZO rundown.
He just gave it to you guys.
So basically, by properly notating your vectors and victors, you can sum them all together. Is that what we're getting at?
Yeah, like a
I like the triangle. I was gonna say I like the triangle explanation you gave earlier, so it really came into play here.
Yeah, it's one page up. It does the triangle math, and that's really all you're doing. And when you're looking at two axes, you're doing triangles. And when you look at three axes, you're gonna take triangles in each double plane and then combine those and run a line between them. But yeah, it's if I have a line, if I would want to draw a vector along two axes, like an XY vector, right? It's like the length of that line in the XY direction, right? The hypotenuse of the triangle, or the right triangle, so to speak, is just going to be the sum of the X and Y components.
Nice.
You add the two X's up and the two Y's up, and you get your total.
Nice.
Yeah. If
Let me see 1 second. Let me see if Scott's mic is fixed. Should be good. Okay, sorry. Go ahead.
I have in mind a vector whose components are 3 and 5. Can you draw the vector for me? If you immediately said it is 3i plus 5j, you're making the assumption that I'm writing the vector in terms of I and j. Now, I agree, I and j point along two natural directions. For most of us, given that the blackboard or notebook is oriented this way, it's very natural to line up our axes with it. But there's no reason why somebody else couldn't come along and say, I want to use a different set of axes. The x and y axes, or I and j, are not nailed in absolute space. They're human constructs, and we're not wedded to any of them. Quite often, it's natural to pick the axes in a certain way to suit the problem. If you're studying a cannonball launched from the Earth, it makes sense to pick the horizontal as the x and the vertical as the y-axis. But mathematically, you don't have to. Another set of rotated but mutually perpendicular unit vectors, I prime and j prime, that form another basis can also be rescaled and added to form any given vector A in the plane. For example, when we study objects sliding down an inclined plane, we will choose our axes parallel and perpendicular to the incline.
Go and give it a little scrolly. There you go.
If I draw an arrow, vector A, on a blank sheet of paper, it has life of its own without reference to any axes. The same vector A can be written either in terms of I and j, which is the old basis, or in terms of I prime and j prime, the new basis. How do the components a sub x prime and a sub y prime in the new basis relate to the components of the old basis? It's a simple problem, but I just want to do it so you get used to working with vectors. They're going to be 90 degrees rotated. For this, we need the very busy figure 2.4. It shows the old x and y axes and the x prime and y prime axes obtained by rotating the xy axes counterclockwise by an angle theta. The unit vectors I prime and j prime are likewise rotated versions of I and j. The components in the two bases are showed by the dotted lines and are simply the projections of A, vector A, along the various axes. We want to relate a sub x prime and a sub y prime to a sub x and a sub y. So if you look at it, you can see how a sub x on the bottom is just shooting out straight to the right, and then a sub x above it is shooting like at some angle. Same thing with a sub y shooting straight up, and a sub y prime shooting at some angle. It's the same offset as between x and x prime is between y and y prime. So we don't know what the angle is, but I'm sure he's going to tell us in a second.
Nice.
First, we express I prime and j prime in terms of I and j using the figure. I prime equals I cosine theta plus j sine theta. And j prime equals j cosine theta minus I sine theta. Here are the details. The vector I prime has got a horizontal part, which is the length, namely 1, times cosine theta, and a vertical part that is 1 times sine theta. How about j prime? It's at an angle theta relative to j. So it's y components cosine theta. Finally, its x or horizontal components negative sine theta, where the minus sign comes because it's pointing to the left along the negative x-axis. All that remains now is to eliminate I prime and j prime in favor of I and j in the expression A equals I prime a sub x prime plus j prime a sub y prime, and equate it to A written in terms of I and j. Scroll down a little. A equals, so he's just transforming. If you look at between 2.18 to 2.21, he's transforming from the prime notation to the standard notation, and he's showing this is these are the expressions that you do to do the transform. And you could do this with any angle. Now, each of those is composed of a horizontal and vertical component. When we equate the coefficients of I and j on the right-hand sides of equations 2.20 and 2.21, we obtain the desired expression for a sub x and a sub y in terms of a sub x prime and a sub y prime. So a sub x equals a sub x prime cosine theta minus a sub y prime sine theta. And then a sub y equals a sub x prime sine theta plus a sub y prime cosine theta. So you can pick your basis vectors any way you like, and so can I. Your basis is obtained from mine by a counterclockwise rotation by an angle theta. All right. Scroll up just a little. The same entity vector A, the same arrow, which has an existence of its own independent of axes, can be described by you and by me using different components. So all he's saying is you can define it however you want. Here's the equation to transform it between the different orientations depending on what your angle of offset is. Your components with primes on them are related to mine by these equations 22 and 23. This is called the transformation law for the vector components under rotation of basis vectors. Now you can ask the opposite question. How do I get a sub x prime and a sub y prime in terms of a sub x and a sub y? The quickest way is to replace theta by negative theta. If we go from the unprimed to the prime system by rotation theta, then a rotation by negative theta is the way to go from prime to the unprimed. The result using cosine negative theta for cosine theta and sine negative theta equals negative sine theta is this, and gives those two expressions. And he just basically flips it a negative on what he had before. And says that turns out to be the correct answer. But I want you to think about another way to show this, which often seems to bother some students. If I told you that 3x plus 5y equals 21 and 4x plus 6y equals 26, scroll down a little bit, we certainly know how to solve for x and y, right? You got to juggle the two equations, multiply the first by 6 and the second by 5, and subtract to isolate x and so on. Why is it then, when some of you see equations 22 and 23, you don't realize it's the same kind of problem, where you can multiply one by cosine theta and then scroll up a little. You can multiply
one by cosine theta and the other by sine theta and add to isolate the a sub x prime, for example. For any particular value of theta, sine theta and cosine theta are just numbers. For example, if I pick theta as pi over 3 or 60 degrees, cosine theta equals 1/2 and sine theta equals square root of 3 over 2. The equations become for this angle these expressions. If you multiply the second by 3 and add it to the first, you obtain a sub x plus square root of 3 a sub y equals 2 a sub x prime, which means these two. He plugs the values in accordance with equation 24. So go forth and treat sine theta and cosine theta as plain numbers and juggle equations 22 and 23 in order to derive equations 24 and 25. Along the way, of course, you'll have to use some of your trigonometric identities, such as the trigonometric identity sine squared plus cosine squared equals 1. The components of the vector depend on who's looking at it. However, there's one quantity that's going to always come out the same no matter who is looking at the vector. It's the absolute length of the vector. It's unaffected by the rotation of the axes. It is an invariant under rotation. You may verify from equations 24 and 25 that all of the, scroll up just a little. Yep. A sub x prime squared plus a sub y prime squared equals a sub x squared plus a sub y squared. I just started at the beginning, went to the end, and he does the math in the middle to equate it. The a sub x, a sub y term is gone since its coefficient is 2 cosine theta sine theta minus sine theta cosine theta. That's just another trig identity. I want to conclude with one important point. We learned that a vector is a quantity with both a magnitude and a direction. A more advanced view of vectors is they're a pair of numbers in 2 dimensions, which under rotation of axes, they transform as per the equations 24 and 25. Anything that transforms this way is called a vector. We already know about the position vector r and the changes in it, with the displacement vectors used in describing the hike. How about more vectors? There turns out to be a very nice way to produce vectors given one vector like the position vector, and that's the following. And then it goes to the next section. But I want to point out equation 2.36. That is the standard way of writing it, and he then changes x and y to x sub t and y sub t, and this is how you change it into physics, from math to physics, right? Because x sub t is position with respect to time in the x-axis, and y sub t is position with respect to time in the y-axis. So he just right here 2.5 is where he transforms this from math into kinematics. So
Well, thank you for reading all that, good sir.
yeah,
Much
sounds more
appreciated.
complicated because he's very wordy and he has to be kind of wordy to like explain it. But it's like it makes a lot more sense if you literally just look at the equations and look at the graphs and don't worry about the words so much. Just let your brain do like patterning and compare and realize what's going on. It's a mouthful to read all that. It's way easier just to like look at the equations and compare them to the graphs.
Yeah, I appreciate your breakdowns. That was really great.
Yeah, triangles, man. It's just triangles.
Everything's a goddamn triangle, it turns out, or some ratio of a triangle. What's up, Bennett?
Hey,
I don't know.
Dr. Bennett.
How you guys doing?
welcome.
Good, brother.
Doing great.
Just saw my Knicks beat the Sixers. Otherwise, I would have been here a little earlier.
Oh yeah,
I saw you were discussing physics, so that's going to attract me.
Heck yeah. Math and physics tonight.
May have been the intent.
I'm glad you're here, Dr. Bennett.
Yeah, thanks for
Hello.
dropping by.
Yeah, I usually see these when they're taped rather than live, but yeah, I came in about 10 minutes ago, and I see you're looking at the physics that supports, the math that supports the physics, and some vector analysis. The Greek letter that I see as phi, I think it's being called theta,
Oh, my bad. Yeah, theta is like an O with a slash through it. Did I call it theta instead of phi? That is my fault.
I wanted to stop you there, but you were
Yeah.
just going. You were in the zone.
Well,
so we
Yeah,
let it
yeah.
roll.
As long
It
as you're
totally is
The thing
phi.
is-
I don't know
with
why I
your
called it
variable.
theta. Totally is phi.
Yeah, sigma 5.
Yeah.
The both letters are circles with a slash through it,
Uh-huh.
and you just have to remember that the horizontal slash is theta.
Yeah. Yeah, I do know that. I don't know why I was being retarded. You're totally correct. I didn't even realize I was doing it until you said that.
The math looked perfect to me, though.
Yeah. Yeah. Basic intro to vector notation for the ether cause boys. Yeah, I
What
think
else
this is
did
great that you
you,
guys are doing this. I think it's great because it's totally awesome for everybody to know physics, right? Because then everybody can start doing like the analysis math.
You'd think so, Piezo.
I assumed that everyone had physics in this group. At least high school physics. Because I'm always impressed with your ability to absorb a lot of information and put it all together.
Yeah, I think the conceptualization's being separated from the math. It's, if a person can understand the conceptualization, that's the important thing. The math, though, to describe the conceptualization is also important, but like not necessarily like when we talk about somebody can know what a vector is without actually working out all the cosine and sine math to like equate the two and transform them. That's kind of the point I'm getting at.
Yeah, it's we kind of have a pretty wide variety of familiarity with the topics of physics and mathematics both. All of us have different levels of depth and breadth of knowledge on both of the topics. So it was suggested to go through some physics stuff kind of from the ground up. And so we were looking for like a textbook to go through, and this book from Shankar was recommended by Eric. And yeah, it seems to be, I guess, this would be technically like a college level physics textbook, it appears. It's kind of nice that it jumped straight into touching on all of this math. I believe what we're doing here is essentially setting up a lot of the foundations for moving forward with the physics concepts is what it looks like.
Yeah.
But that was cool to touch it down on, vector math, and we touched on calculus and a little bit of trig there. Good stuff. Who would have thought that flat earthers would get together and, like I already said earlier, get together and argue about vector math notation for 15 minutes?
This is why I think math fight's a good idea.
Dude, I wish like the funny thing is like the first two courses of physics is pretty much all of classical mechanics. Like you cover the entirety of classical mechanics in 2 semesters, and then after those first 2 semesters, then you start getting into like electromagnetism. But if everybody was to take 2 semesters of physics, they would have sufficient knowledge to be able to do just about anything they need to in the real world. It only stops being possible to do everything in terms of when you get into like circuits and stuff. But any type of like motion or anything like that, you know everything. In
Yeah,
2
it's what's the
semesters.
old quote is the only I probably gotta butcher the quote, but the only real science is physics. Everything else is bookkeeping.
And you only need to know a little bit of calculus in order to be able to do it. Like if you have a trigonometric identity table and you have an integral table, you only need to know how to do a derivative and how to do an integral. And then you can do physics. I mean, in physics too, you start getting into double integrals, which technically like that incorporates, 3 axes. Because you're going to have the inside integral in one axis, two axes plane, and the outer integral and another 2 axes plane to get the overall 3 axes integral. So you do need a little bit of like Calc 3 for that, but the concept, right? Like without being able to do the math, like you can still understand the concept of what's happening, right? And I think that's the most important part. The math is a little more difficult, like because you actually have to take courses to be able to compute it. But I think as long as you can understand the essence of what's happening, it will go a long way for helping you get like how they're calculating stuff.
For example, when we started with the kinematic derivation of G, and we didn't quite recognize it because they kept moving it around algebraically. It's like, well, no, it's still that they started with the same thing that we always start with: height equals half acceleration times squared plus velocity times time, right?
Well, it's the same thing. Like the statement I just made, it applies universally because, like, if you think about Einstein, right? I have not personally taken the coursework for relativistic math. I can look at it and be like, oh man, there's some really long equations, and I haven't actually crunched the numbers myself. I haven't done problems in a classroom practicing how to do it, but I can look at it and see the essence of what's going on without having computed it. So that's kind of what I mean with this. Like, you might not be able to compute it if you aren't sharp enough on your math or haven't practiced enough, right? But like, you can learn the essence of it separately from learning the computation. That's kind of what I mean. And I think the essence is the most important part. In fact, I think you can learn the essence first and then learn the math after. And if you've already learned the essence, you go into a classroom to learn the math, it makes learning the math way easier.
They both kind of make each other easier. It's interesting how that works. You learn to do the computations, it makes it easier to understand what's going on conceptually. And if you learn the concepts, it makes it easier to understand the computations. At least that's been my experience.
Maybe it's personal preference. For me, it's easier to learn the essence first. Like anytime I've learned the pure math first and then tried to apply it later, it's like a much harder process. If I like go over the concept and the essence first and see what's happening and then try to plug the math in after, I've always been able to learn stuff like way faster that way. But everybody's different.
On that note, I would recommend if anyone wants to watch some linear algebra videos or some calculus videos, the 3 blue, 1 brown Essence of Calculus and Essence of Linear Algebra series is really, really, really fantastic, specifically for doing what Piezo is describing there as far as just explaining what they're doing with their math. Not necessarily teaching the calculations, but just the meaningful side of it.
Well, I'm going to go cook now, boys. A little past my cook time, but it was worth it.
Later, G. Much appreciated.
Yeah, right on, man.
Yeah, I'm gonna stay tuned in on my phone, but I'm gonna mute up.
Well, I think we're going to wrap up the reading with that. Made it to a nice, even 44 pages. Very nice.
Very nice. Wow.
Wow. Yeah, actually.
That's
Go ahead
awesome,
and close
actually.
that out. So, are there any final thoughts before we wrap up for that?
So about the role of math in physics, I think a lot of the problems with mainstream physics is that some of the physicists have gone overboard in the mathematics, especially in areas like general relativity. And they've lost focus, like you said, on what reality is. Physics is based on the scientific method, and that's the key, being able to connect whatever your theory is with reality. And yes, math is an important tool in physics, but it can be abused in the sense that, what's the word? You can try to snow other people. You can try to bury them with mathematical detail when you're not clear about in your understanding of what the reality is. Anyway, that's my 2 cents, and I
Math
look
as a
forward
weapon.
to looking at the tape.
Thank you, Dr. Bennett. Yeah, like the example we read earlier, right? The having the radical sign expression, and obviously there's a plus or minus, and it was for energy, and he's like, oh, you don't think of energy as being negative? It's always a positive quantity of energy, but the math is the math, and so it means there must be antiparticles, right? There's
Yeah,
like a
exactly.
fundamental flaw in your logic because I mean, who said it was particles in the first place? It was a wave function. So maybe it's just like a maybe it's like a forward and backward, or maybe it's a spatial and a counter spatial, but you're over here thinking it has to be a particle and an antiparticle because you made math your basis instead of physical reality.
Well, Dirac was correct in saying that the negative solutions to his equation could represent a particle. And then what was it? 4 years later, they discovered the positron, the positive electron. So sometimes the math unfolds a new reality, and in that case, it was true.
Well,
Positive electron.
The math was true, right? There was something that needed to be accounted for. That much was true.
Oh, for sure.
Absolutely. But their description is, yeah. I would say, what's the word? It
Contentious.
leaves you wanting.
Mm-hmm.
It's not
Yeah,
quite
no.
describing things in a very eloquent way. You know, antiparticles, things that we can't really observe, we can't really quantify, we can't really attribute any mechanics to, but we need them for our math, and so as such, we're just going to call them something real.
We get a reading, we get an energy reading on a screen, and we see that that energy reading is the perfect offset to make the energy of an electron balance out on the other side of the equal sign. So we presume that there's a particle that's just an inverse polarity of an electron there. But we never actually measured a particle. We're just doing mass energy conversion the entire time. So it's
Well,
like
the way they discovered the positron was to produce a beam of them and notice that when the electron in the magnetic field turned left, the positrons turned right. So they were the same weight or mass as the electron. So it seems that there is a reality there. It's not just a solution to a math equation. That maybe you're thinking of solutions to equations where you get imaginary numbers. You get the square root of -1.
Well, I'm just saying the physical explanation leaves room for leaves you wanting for more, because really they're not properly looking at their fundamental, the foundational precepts that they set out with when they asserted particles in the first place.
Yeah, I agree with both of you. Like, yes, 100% they're observing something that's fundamental here, right? We have what we have described as an electron beam that always deflects this certain way, and then we've created another beam with an inverse polarity that deflects the other way, so we presume it to be fundamentally of the same character and nature as the electron, just inverse polarity. But I think where the disconnect is how did they know, right, in the first place? Like, what was their basis for, finding the electron? And if you trace that all the way back to like the cathode ray tube experiments and then the things that built on that, there's not actually any independent exclusive evidence for electrons themselves. J.J. Thomson could have easily interpreted his experiment in terms of a wave and come to the same math and the same conclusions. And in some people's opinions, it would have fit better, such as the fact that the cathode rays were observed to pierce through solid materials, which doesn't sound like a bunch of billiard balls, right? Because billiard balls ought to bounce off a solid metal wall. But then they say, okay, we're going to later, 20, 30 years later, after we get Schrodinger wave equations broken into quantum mechanics and get probability distributions, we're going to say the reason that happened was because there's a probability distribution and there's a certain percentage chance that the electron could pass right through the lattice structure of the metal and just come through the other side. And so they do stuff like that, but it's like, what's the simpler explanation? I can see how a wave passes through metal. I can strike a metal beam with a hammer and feel the vibration come through the other side, right? So it makes perfect sense in a wave context. Also, the fact that we've never observed electrons to experience downward acceleration due to gravity, which must necessarily affect all objects of mass. And since electrons are considered a massive object, they ought to experience the acceleration in a gravitational field, and specifically that they're known to not do that. Now they explain it away with, the magnitude of it is so small because they're so light, they're so small mass that we shouldn't notice it, but it's like because they're overcome by the other forces in nature. But I mean, if we were to isolate it into a vacuum chamber and blah 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 blah, blah super careful, super sensitive experiments, blah 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 blah, we ought to be able to isolate that,
Never thought of that. That's the mass of the electron. How is it determined experimentally?
He determined the. Oh, sorry. Were you telling or
Go
asking?
ahead. Well, to me, the big philosophical question with antiparticles is, why is the world basically totally composed of koino matter, that is, normal matter? And why isn't there an equal number of antiparticles that are visible? We have to strain to create enough energy to create antiparticles. And in other words, why isn't there a balance in nature between the two, rather than the tremendous imbalance that we observe? As far as I know, that's one of the problems that that physicists and scientists explore.
Yeah, I'm not actually equipped to answer that at this current moment because I'm not sure all the exact specifics on when they create the like positrons and things like that. I would have to look more into the experimentation. But I do know that when they did the math to derive the electron, what they basically did is they took the Lorentz magnetic force law, and they combined that
F
with
equals QV cross B.
Yeah. So and then it simplifies to FB equals E times V times B, right? And then they combine that with the centripetal force law, right, which is mass times velocity squared over r. And then they combined that with the kinetic energy law, and they crunched them all together to and did kinematic manipulation, and then plugged in the charge mass ratio of the electron on one side of the equation and solved it in terms of E over m, which is charge over mass, and then they derived the charge mass ratio. But that operates off the fundamental presumption in the first place that it's even appropriate to plug in the centripetal force equation, because the centripetal force equation incorporates a mass involved. If that beam of electricity is not made up of a bunch of little things of mass, then it's a fundamentally wrong, erroneous thing to do in the first place to even use a centripetal force law, right? You're already assuming it's made of mass in the first place when you plug that into the setup. So that, in other words, they used equations that accounted for mass presumptively when they did the experiment and did the charge to mass ratio, when if it's not actually made of mass in the first place, all you're doing is playing make believe. They basically solve for, if this beam of electricity was made of mass, here's what the relationship of the mass would look like.
Yeah, it sounds like you're a wave theorist. That I guess you're looking at everything from a quantum point of view as probability waves.
Actually, from classical waves, like Schrodinger waves. Schrodinger, was the one who made up, not made up, but derived these equations, and they'd used his equations to create, the quantum mechanics explanations of things with the probability distributions. But he himself commented on all that and said it was a bunch of make believe and it was a bunch of nonsense. And he said that that the equations. He said that the equations themselves were actually meant to describe a physical reality, and that they were energy waves, like they were actual waves of energy within a medium. And so what
The
they were doing,
superstate is hypothetical. Yeah.
right? And what they were doing by squaring that wave function to get a bunch of points, right? Turning a continuous wave into a discrete point system, creates a bunch of conundrums like quantum state superposition, where you have one particle in multiple places at the same time, or multiple particles in one place at the same time. And it's like, that doesn't make any sense. So they say it's just mystifying and weird, and the quantum world is weird and operates differently. And it's like, no, if we actually look at this graphed out, you have to have two particles in one place at the same time without colliding or bumping off each other. But I just have two waves that approach each other, combine to form a double amplitude, pass through each other, and then continue on their merry way. So which one makes more sense?
Yeah, but the superposition of the waves is just at an instant of time. You must account for the persistence of mass through time, not just the creation of mass by the positive reinforcement of two overlapping waves.
It occurs for a finite time. It has a maximum intensity at one point, but it has a relatively changing intensity across the entire convergence time. But that's kind of straining at gnats. My greater point was that there's a lot of presumptions built into what they've done. We've never isolated an electron and measured it, weighed it, right? Everything is done through mass energy equivalence, which is also presumptive. So if we go back to square one and we were to have to do all this over again, we didn't presume that it was already established. If we just said we're going to redo the physics for ourselves and figure this stuff out, and we didn't operate off of particle assumptions, if we only just did this with non-presumptively, we wouldn't. I don't think that we would. It would necessitate the particle concept, because if you don't have mass energy equivalence, you can't even come up with particles in the first place. And sure, if you presume mass energy equivalence, you can build a system of discrete functions with a bunch of points. But what if it's not made of particles? What if mass and energy cannot be, switched back and forth? What if that's not a thing that you can actually do? Then that just means everything you're doing is just made up in the first place. So that was kind of my point. J.J. Thompson's 1882 paper. I'm gonna drop it in here for you. I think you'd love to read it. Before he made the electron theory in 1897, because he was chasing that Nobel Prize, he won another award for a paper called A Treatise on the Motion of Vortex Rings. And in that paper, he actually he demonstrates, first he demonstrates like 100 pages of integral math on how the motion or how the vortex rings would behave. He postulates it as a theory of matter, of the origins of matter, as basically vortices within a fluid medium like the ether. He does the math on how the vortexes could link together. I just put it in there. Let me tag you. Do you see it in the chat?
Oh, let's.
Here, I just tagged you.
Gotta pop up his adjust your soundboard volume.
If you click at the top right, at the very top right of the Discord window, there's a little box. It should have a little red circle on it. It says inbox. If you click that, it'll say mentions, and then you'll see my mention.
I see Shane's May 2nd.
Here, I'll just DM it to you directly.
It's in the live chat room.
Yeah, it's in the live chat in our Ether Cause live chat. But anyways, he shows how if you link these vortices together, he's like, we can link 3 of them in a triangle, 4 of them in a square, 5 in a pentagon, 6 in a hexagon, so on and so forth. He maths it out and shows that a hexagon is the largest stable configuration. Once you get to 7, the stability breaks down. It's no longer stable. And what we've learned since then, using tunneling electron microscopy, is that when we look at the lattice structures, like subatomically, or not subatomically, but microscopically, of matter, a hexagon is actually the largest natural lattice structure you find in nature. You don't get heptagons. Heptagons become irregular and non-uniform and can't hold strain. And a hexagon is actually the most condensed form of a lattice of a regular lattice structure where it minimizes free space. There's like no gaps, and in fact, anything above a hexagon, you pretty much have to do material engineering and do a bunch of crazy stuff in a lab to force it to be formed. And they do have like synthetic compounds that they've made and synthetic hydrocarbons and stuff where they've been able to incorporate like an octagon here or a heptagon there, like using, you know, modern 150 years later physics, but his fundamental concept that he made, conception was actually accurate. And this was without him ever, he mathed it out basically before we ever knew about it. And he also solves the gas pressure problem of the ideal gas law using the vortices as well. And he's like, hey, the ideal gas law, we know that, you know, no pressurized system ever actually ends up having that amount of pressure. It's always a little bit less. We know this, like experimentally, it's always a little bit less, but actually, if we think about the math in the kinetic theory of gases, you've only got two options. You either got perfectly, you know, elastic collisions conserving the momentum in the system, which means that there should be no deviation whatsoever. He's like, or you have the intermolecular forces theory, where as they approach really close to each other, they repel each other, right? Like we think about electron clouds repelling each other, right?
Hey, real
He's
quick,
like,
Piezo, I hate to interrupt you, and please, I want you to finish your thought, but let's also, I'm just really happy to have Professor Bennett here, so if we get a chance to just make sure let's make sure we give him a chance to respond, and if anyone has any, also I would just say if anyone has any specific questions they want to ask him, let's make sure we give everyone a chance to do that.
sorry, man, I wasn't trying to monopolize the mic.
No,
Yeah,
you're good. I
I'm
get
almost
it. I get
finished.
it. Go ahead.
And then if we assume the intermolecular forces theory, then actually the pressure should always be just a little bit greater than the ideal gas law. And if you think about it, you know, take a super pressure container, squeeze all the gas particles really, 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 really close to each other so they're almost touching, they're almost rubbing inside the container. That means that the electron clouds should be repelling each other, right? Which actually would add to the pressure in the container. So it wouldn't be PV equals nRT. You know, it'd be like PV equals nRT plus repulsion. So it should cause a deviation in the positive direction. But in actuality, any pressurized system always has a pressure that's slightly less than the ideal gas law, 100% of the time. And this is still true 150 years later. It's a known problem in gas theory. And he postulates how, if you look at it in terms of vortices, after all these 100 pages of math I've done, look right here, you actually get this double integral, and this accounts for the little bit of a deviation in the negative direction. He's like, it matches the math. So he thought that his theory in 1882, 1883 was a much better theory than the atomic theory, than the kinetic theory of gases. He proposed an experiment to look at the difference, to draw a distinction in the two, to figure out which one was really true. But the experiment was never done because 4 years later they did Michelson-Morley, and everybody started freaking out. And then they started moving really heavily towards particles because they didn't want to do waves in a medium anymore because it meant the Earth wasn't moving. So J.J. Thomson was on the right track, and then decided he wanted the Nobel Prize, I think, and that's why he went away from his, you know, giant treatise on everything being made of waves in the ether and switched to being a particle boy. So I gotta go. Yeah.
Yeah, thanks, Piezo. Any thoughts, Dr. Bennett?
But yeah, there was a lot of things covered there. I know that the tiling problem, which is mathematical, was solved by the heptagon in 3 dimensions. It's the largest shape that you can pack a 3-dimensional space without, as you said, any gaps. Going back to the beginning, I do recall now the cyclotron experiments where they put electrons into a magnetic field and equated the centripetal force to the magnetic force and got the ratio of E over M. Millikan had measured what the charge on the electron was, and so having E over M and knowing what E is gave them what M was. It certainly wasn't putting electrons on a scale and trying to measure it that way. I'm not sure who was talking. Was that Pizzo or?
Yep.
Okay, Pizzo. All right. Yeah, a lot of interesting topics, and Alan, I'm still working on the gee,
The old Ether
what's the
Press.
name?
The
No,
Hildebrand.
Hildegard.
Hildegard.
Oh.
Yeah.
Yeah,
Yeah,
the
looking forward
Hildegard.
to it, man.
Yeah, I'll be sending you an email soon with preliminary slideshow and
Nice.
some other requests. So I have other things like Knicks and the Derby is on Saturday, so I have to use a mathematical analysis to try and pick which is the winner out of 20 horses.
Nice.
Yeah.
Nice. Hit him with a
Always
little
a
Hamiltonian.
yearly challenge.
Nice.
Dr. Bennett, would you have any interest in reading a 1968 paper that was published in Nature with the title Experiments to Determine the Force of Gravity on Single Electrons and Positrons?
Not exactly in my ballpark, but yeah, I'm interested in all phases of physics. So I don't know how you can pass that to me.
You have your direct messages. I could do that. DMs.
Right. I know how to do that. Yeah.
Okay. Let me try to send it to you. I didn't want to overload you with, a lot of papers but if you have an interest, let me see if I can get it to you right now.
All right.
Yo, do I hear the legend himself in the house?
We lured him with physics, so. You said you're gonna have a new tides paper too, as well. I think. Not to overload you.
Okay, here it comes. Watch out.
Well, I guess maybe should we close out our streams?
Yeah, 3 hours.
Let's go ahead and do that. We can have a more casual conversation here afterwards. But in any case, thanks everyone for being here for Ether Cosmology Reading Night. We got pretty far into Shankar's Volume 1 on physics, and I found it to be a pretty enlightening discussion. And what do you know? You talk enough math, you talk enough physics, and Bennett just can't help himself. So we might have to do some more of this. But yeah, and thank you so much for being here, Bennett. Dr. Bennett, did you have anything, no pressure whatsoever, but is there anything that you would want to say before we close out our streams to any of our listeners? Cool. Oh, go ahead.
No, I really appreciate your interest in Ether and your activities. I'm glad you introduced me to your channel on YouTube and to the Discord. And I hope we can work together and maybe discover some new things.
Nice.
Excellent. Well, thank you. As you can tell, I mean, hopefully it's apparent that we have an immense amount of respect for you and your work, and we're thrilled to have your works to dive into and to use to further our argumentation and to just look at objectively and try and take an objective approach to science. So thank you for your work. And so thanks everyone for being here again. Oh, go ahead. Was someone going to say something?
Nah, we're wrapping it up. B,
Cool.
check us out tomorrow on Flat Earth Fridays at
There you
8.
Alan wants to go.
Later, G.
Take care, everybody. Thanks for being here.
All right.